Astronomers have long known that the universe is structured like a vast cosmic web, where galaxies gather along long filaments separated by enormous empty regions called cosmic voids. For many years, these voids were mostly considered simple gaps between the universe's major structures, but recent discussions in cosmology are drawing renewed attention to them. Scientists now think these vast regions may actually be where the universe's accelerating expansion is most strongly unfolding, driven by the influence of dark energy. If that idea holds, the emptiest parts of the cosmos could be quietly shaping the long-term evolution of the entire universe. In this video, we will explore what cosmic voids are, how they grow, and why these immense empty regions may be slowly pulling the universe apart. Let's get started. When astronomers map the universe on its largest scales, they see a striking pattern. Galaxies are not scattered randomly through space. Instead, they form an intricate network called the cosmic web. In this structure, galaxies line up along enormous filaments that stretch across millions of light years. These filaments intersect at dense clusters of galaxies. Between them lie vast regions where matter is extremely sparse. These regions are known as cosmic voids. Cosmic voids are among the largest structures known in cosmology. Many span tens to hundreds of millions of light years across, yet contain very few galaxies compared with the cosmic average. Early in the study of large-scale structure, astronomers viewed voids mainly as byproducts of gravity. As matter collapsed into filaments, walls, and galaxy clusters, empty regions were naturally left behind. In this picture, voids were simply passive gaps created by the clustering of matter. However, observations and computer simulations have gradually revealed a more dynamic picture. Cosmic voids do not remain static. Instead, they expand over time. Matter slowly flows away from these low-density regions and toward the surrounding filaments and clusters. As this happens, voids grow larger, while the structures around them become more pronounced. This behavior means voids are not just empty spaces between galaxies. They are evolving components of the cosmic web. The discovery of cosmic acceleration in 1998 added another important layer to this story. By observing distant supernova explosions, astronomers discovered that the expansion of the universe is speeding up. This unexpected result led to the idea of dark energy, a mysterious form of energy that appears to drive cosmic expansion. In regions rich with matter, such as galaxies and clusters, gravitational forces dominate local behavior. But in cosmic voids, where matter is scarce, gravity has far less influence. This allows the effects of dark energy to become more visible. Because of this, many cosmologists now view voids as environments where the expansion of space, driven by dark energy, can proceed with minimal interference. As the universe evolves, these expanding voids gradually press against the surrounding filaments of galaxies, subtly reshaping the large-scale structure of the cosmos. Cosmic voids have become increasingly important to cosmologists because they provide a unique environment for studying one of the biggest mysteries in physics, the nature of dark energy. Dark energy is believed to be connected to the energy present in empty space itself. According to quantum field theory, space is never truly empty. Even in the absence of particles, fundamental quantum fields still fill every region of the universe. These fields contain a small amount of energy known as vacuum energy. In Einstein's theory of general relativity, energy influences the curvature and expansion of space-time. If space itself contains energy, it can contribute to the overall dynamics of the universe. In the standard cosmological model, this effect is described by the cosmological constant, represented by the Greek letter lambda. Combined with cold dark matter, this forms the widely accepted lambda CDM model of cosmology. According to this model, dark energy acts as a constant background energy that causes space to expand at an accelerating rate. However, Dark energy remains one of the least understood components of the universe. Scientists still do not know whether it is truly constant or whether it changes over time. It might represent a property of space-time itself, or it could point toward entirely new physics. Studying dark energy directly is difficult because most regions of the universe are filled with matter. The gravitational interactions between galaxies, dark matter, and clusters complicate measurements of cosmic expansion. Cosmic voids offer a different perspective. Because these regions contain very little matter, the gravitational influence of galaxies and dark matter is weaker. This makes voids particularly useful for studying how cosmic expansion behaves in environments where gravity plays a smaller role. Astronomers analyze voids by examining how galaxies move near their boundaries, how the shapes of voids evolve, and how quickly these regions grow over time. These observations allow researchers to test whether the universe expands exactly as predicted by current cosmological models. Some researchers have also explored whether the distribution of cosmic voids could influence how we measure the expansion rate of the universe. This idea has occasionally appeared in discussions surrounding the Hubble tension, a disagreement between different methods used to calculate the universe's expansion rate. One possibility is that living within or near a slightly underdense region could subtly affect certain measurements of cosmic expansion. While this explanation remains debated, it illustrates how the structure of the universe itself may influence cosmological observations. For now, the majority of evidence supports the standard dark energy model. Still, cosmic voids provide a powerful laboratory for testing both established theories and new ideas about the physics governing the universe. If cosmic voids continue expanding under the influence of dark energy, they could play a major role in shaping the long-term structure of the universe. Over billions of years, voids gradually grow as matter flows outward towards surrounding filaments and clusters. This process stretches the cosmic web and increases the distances between galaxies. As the expansion of the universe accelerates, these effects become even more pronounced. Galaxies and clusters drift farther apart as space itself expands. In the distant future, this process may dramatically alter the appearance of the universe. Large-scale structures will become increasingly separated, and distant galaxies may eventually move beyond the observable horizon. If this trend continues, the universe may slowly evolve into a much emptier environment than the one we observe today, with isolated galaxies surrounded by enormous expanding voids. Understanding how this process unfolds requires precise observations of cosmic structure. Several major astronomical projects are currently working to map the universe in unprecedented detail. One of the most important upcoming missions is NASA's Nancy Grace Roman Space Telescope, designed specifically to study dark energy and the large-scale structure of the cosmos. By surveying vast areas of the sky, the Roman telescope will measure the distribution of millions of galaxies and identify thousands of cosmic voids. These observations will allow scientists to track how voids grow and how their expansion relates to the overall expansion of the universe. Ground-based surveys are also contributing valuable data. Instruments such as the Dark Energy Spectroscopic Instrument, or DESI, are mapping the three-dimensional distribution of galaxies across billions of light years. These surveys provide increasingly detailed maps of the cosmic web, revealing both the dense filaments of galaxies and the enormous voids between them. With these new datasets, astronomers hope to refine measurements of dark energy and test whether it behaves exactly as predicted by current models. If future observations reveal deviations from theoretical expectations, they could point toward new physics beyond our current understanding of cosmology. Cosmic voids may look empty, but they could be the regions where the universe's expansion is most strongly unfolding. As these vast spaces grow, they slowly stretch the cosmic web and push galaxies farther apart. By studying them, scientists may uncover key clues about dark energy and the ultimate fate of the universe.